Yeah, спасибо. So it's going to be an alternating sum of all the ways to multiply these things together. Okay, so what is this? There's a plus in front of this. There's a minus in front of multiplying G1 on G2. Then I'll have, toward the end, I'll have minus 1 to the n minus 1. And on the very last term, I'll move the gn off the end. So this will be minus 1 to the n, g1, gn minus 1. And here, this would be multiplied by gn on the right, but it's kind of acting on a copy of the trivial representation. So it just becomes a 1. Okay, so that's an operator, which goes from bn to bn minus 1. And you can check that this is 0. That squares to 0, so I get a complex. And you can also check that there's a subcomplex. So likewise, you can define the reduced version of this, b bar n. So there will be now n copies not of zg, but of zg bar, where zg bar is zg modulo z. Okay. And you can check that there's a subcomplex of this complex where one of these, at least one of these entries is 1. So you can check that there's a subcomplex of b. I probably should write b lower n, because this isn't homological grading. So there's a subcomplex of here with a basis of elements of the form everything where there's some 1 in the middle somewhere, or maybe at the ends. And the quotient by this subcomplex this makes these reduced bar expressions into a complex. The differential is just like this, except that when you compute the differential, if somewhere in here a 1 appears, it just becomes 0. Okay, so we'll see examples of that. And the proposition, which is not hard to check, but we'll leave it for this seminar because it's not hard to check, is that b dot g and b dot bar g are exact, except on the in degree 0, where I just get the trivial module as the homology. So these are projective resolutions of the trivial module. In fact, we'll see, I mean, the proof is actually to construct a null homotopy. There's an explicit null homotopy. Of B dot or B dot bar of the resolution. So you extend it, you extend the complex by the augmentation. There's a null homotopy of that, so the augmented complex therefore is quasi-isomorphic to 0, so it's exact, it's a resolution. So we'll check this in the seminar, it's not hard. So let's take this as given. We have our resolutions. And so we can use this resolution to try to compute these things, to write down explicit co-cycle representatives, write down the co-boundaries, and so on. So let's try to do this. Okay? So I'm going to prefer to use this reduced version, but I could use the other version. But I'll use the reduced version because it's a little more transparent how things work out. So let's compute, let's do examples of co-cycles and co-boundaries. So let's do degree 0. So what's the complex in degree 0? N equals 0, so I just have a copy of ZG. Right? So a cochain a 0 cochain is just a map of modules from the group algebra to A, but it's supposed to be a map of modules, and a map of modules from a ring to a module, it just tells me where 1 goes. So the cochains are just elements of A. Okay? And then there are no co-boundaries because there's no -1 term of this complex. So there are no co-boundaries. Since the -1st term is 0. However, there's a condition for a cochain to be a co-cycle. So let's write down the co-cycle condition. So when is this a co-cycle? Well, if I precompose with the differential, it should become 0, right? And what is the differential? So I have, in degree 1, my basis elements look like this. And my differential sends that to G1 minus 1. Okay, so I have this first term is like G1 blank minus blank times 1. Okay, and then so let's call this alpha. And then my alpha sends that to what? So it sends it to G1 times alpha 1, which is A, minus alpha of 1, which is A. So the co-cycle condition is that this is 0. Okay, alpha is a co-cycle precisely when this expression is 0. And this happens, so the conclusion is that the reduced 0 co-cycles of G with coefficients in A, they're elements A such that G times A equals A for all G. And those are exactly the invariants. This is A such that G dot A equals A for all G. Very good. What's next? So that was 0 cocycles. Let's do degree 1. I'm going to, don't let me, well, maybe I'll erase that. But I'm going to want to save the degree 1 and degree 2 stuff for use later. So I'm going to write it here and shout at me if I start erasing it at some point. So let's write degree 1. Okay, so what is a reduced 1 cochain? It's a map from the degree 1 part of our resolution to A. It should be a map of modules. This is free as a module on this. So that's the same data as a map from G. This labels the basis here, except that it's reduced. So it's a map like this, such that alpha of 1 should be 0. Right? Given such a thing, I can define this by defining it on the basis via alpha. So that's what a reduced 1 cochain looks like. Let's write down a coboundary. Okay, so a 1 coboundary looks like the following. Suppose alpha, let's say beta of 1 equals A, so this is a 0 coboundary, is a 0 cochain, and then I want to take the differential of that. So then the differential of such a thing, it evaluates on one of these guys. How does it evaluate? It's beta of, where does the differential send this? It's this G minus 1. Okay, so what is that? That is G dot A minus A. Okay, so a alpha is a 1 coboundary if its value on G is of this form for some fixed A. So that's 1 coboundaries. What are the 1 cocycles? Okay, so what do? So given alpha, when is it a 1 cocycle? It's supposed to vanish on the differential of something from degree 2. So what is the differential of something of degree 2? I need alpha, so I want 0. Should be alpha of D of G1 bar G2. This is, we have the formula there, G1 times G2, so this will be G1 alpha G2 minus alpha G1 G2 plus alpha G1. Okay, so that expression here is supposed to be 0. That's the 1 cocycle condition. Okay, very good. Equivalently, it might be nice to rewrite that in the following way. I like to say what alpha does to a product. well, it's not a homomorphism. It should pull out G1 like this. And you can interpret this as there's a G2 acting on the right, but it's acting trivially. And then this would be like the Leibniz rule. So this is the kind of Leibniz rule. Where the right action of G is trivial. So A is a G module. G maybe acts non-trivially on the left. If I force it to act trivially on the right, then this would be just the Leibniz rule. So such a thing is called a derivation. So we could also say one cocycles are derivations. Okay, so let's do degree 2. Are there any questions about degree 1 before we do degree 2? So just kind of an exercise in the definition with the differential. So degree 2 of reduced 2 cocycle by the same logic as for a one co-chain. This is a map of pairs of group elements with values in A. Such that alpha of G1 and alpha of 1G should be 0. So that's the reduced part. It's saying that it actually comes from a map out of this for n equals 2. Okay, so let's write down the co-boundary condition and the cocycle condition. So a 2 co-boundary is something which is the differential of a 1 cochain. So let's say beta from G to A with beta of 1 equals 0, a 1 cochain. Then what does its differential look like when evaluated on a pair of elements? Well, this is beta of the differential applied to this, which is G1, G2 minus G1 times G2 plus G1. Okay. Which is, remember, beta is G linear, so this will be G1 G2 minus beta G1 G2 plus beta G1. So co-boundary, a 2 cocycle, a function of 2 group elements like this, it's a 2 co-boundary if there exists a 1 cochain, so that the 2 cochain is given by this formula. Okay, so let's look at a 2 cocycle. Now we have to consider a triple of elements, right? So alpha, our 2 cochain, will be a 2 cocycle if there's going to be some condition. It should be that 0 equals alpha of D of a triple for all triples. what is this? This is going to be G1 of alpha G2 times alpha G2 G3 minus alpha G1 times G2 comma G3 plus alpha G1 G2 times G3 minus alpha G1 G2, and G3 gets moved off the end and acts trivially on the right. Okay. So our two-co chain like this is a two-co cycle if and only for all these triples. This expression here is 0. That's what the formula tells us. And we're going to see that it just looks like some formula, and we just computed it mechanically. But we're going to see it actually has some meaning. So let's first interpret one cocycles modulo one coboundaries. Sorry? I'm saying alpha is a two coboundary if there exists beta such that alpha of G1, G2 equals this expression. So I can draw it. Let me draw it. What are we saying? So here is my two-co chain. And I want to know if it's a coboundary. Being a coboundary exactly means, so this is the differential, it exactly means there exists a beta, so that alpha equals beta precomposed with D. And that will be true if and if it's true on all basis elements. And what we've written here is the condition on basis elements for this to be true. Well, let's compute. I'm saying this. So here, if I take a basis element here, I'm saying alpha of a basis element of the form G1, G2. That's supposed to be equal to this expression. So D of G1, G2, beta. There's supposed to exist a beta for which this is always true. And then I have a formula for this. This is beta of G1, G2 minus G1, G2 plus G1. What's that? One of them is this D, and one of them is D in the cochains. So this is D in the resolution. So let me write it like this. So this one is in the cochains. And this one, where did it go? I mean, I just kind of spelled it out. This is D of B lower. Right? Like when I hum out of a complex, I get a new complex. It has its own differential. So this D of beta is the differential in that hum complex. And what appears inside the brackets is D in the original complex, out of which I take the hum. because the differential in the Hom complex is defined by precomposition. Okay. So let's interpret these expressions. So cohomology in degree 1 has a pretty simple interpretation. So let me give a definition. So given a group G and a G module A derivation is a map, let me call it delta, little delta, from G to A, such that delta of G1 times G2 equals G1 delta of G2 plus delta of G1. Okay? That's just the definition. You can think of that as the Leibniz rule if you understand that G2 is there acting, but it's acting trivially. And a derivation is called principal if it's of the form little g goes to G acting on A minus A for some A. Okay. And then proposition, well, let's say notation, you can check that if you add two derivations together, you get another one. And same for principal derivations. So you can check that der G A, the derivations form an abelian group under addition. And der, I'll call it der sub 0 maybe, G comma A, the principal derivations. Form a subgroup. And then by this calculation, we saw that the one cocycles were exactly the derivations. And the one co-boundaries were exactly the principal derivations. Okay? So proposition H1 of the group with coefficients in A, its derivations modulo principal derivations. Okay, and one reason I'm telling you this is that there's a kind of pattern. Derivations appear in lots of different contexts. Here they're appearing for a group with values in a module. They also appear for Lie algebras, for commutative algebras, for non-commutative algebras. And you'll often have some cohomology group expressed as derivations modulo principal derivations. So this is one example of this phenomenon. I also want to interpret derivations an additional way, a kind of, I don't know, more geometric way, if you like. So I'm going to have a little digression about extensions. And then that will be related to H2, but it will also give us a different interpretation of derivation. So given again G a group, A G module, an extension of G by A I'm going to say this, but I want to first make an observation. Observation. Suppose I have a short exact sequence of groups. So given a short exact sequence of groups, so in the middle, I have some group G tilde. It has a quotient G. And I want to presume that the kernel is abelian. That doesn't always happen, but let's suppose we're in a case where it does. And because it's abelian, I like to write the multiplication of the group actually as addition, and so the unit is 0. Okay? So with abelian kernel. Okay. Then the observation is that there's an action of G on A. So A is actually a G module. So then claim A becomes a G module. Via the following. So G dot A is defined to be, I choose a lift of little g to G tilde, any lift, and I conjugate inside of A. And so certainly if I apply the quotient inside, it's a homomorphism, so this will go to little g. This is in the kernel, so it'll go to 1, and this will go to little g inverse. So it'll all cancel out. So conjugation like this stays in the kernel. And you can also check that if I chose a different representative, it wouldn't change this, because A is normalized in abelian. Okay? So you can check that that's an action of G on A. And so anytime you have a short exact sequence with a abelian kernel, you're looking at, among other things, this one I can erase. This one I want to keep. At least this one, the 2 cocycles. We've already dealt with the 1 cocycles. Check. Okay, it's not hard. So that's a little exercise for you. We can talk about it more in the seminar, but it's easy to check. Okay, so the definition is the following. We kind of want to reverse this process. Fixing G and fixing A as a G module, we want to look at all ways to build short exact sequences like this. So given a group G and a G module A, an extension of G by A is a short exact sequence of groups like this. Such that the action of G that you get on A is the one you started with. Action of G on A given by the extension data is just the original G module structure, is the given action. So maybe there are many actions of G on A. We want this one to be the one we started with. We'll do some examples. Right. So this is what an extension is. And there's an obvious notion of isomorphism. So an isomorphism of extensions is the following. So I have one extension. I have a second extension, G tilde prime. I want the two outer bits to be fixed, so it'll be the identity on those. But in the middle, there's maybe some non-trivial isomorphism. So just like we did for extensions of modules, but now where G and maybe G tilde are non-abelian. And we also have a notion of trivial extension or split extension. Okay, so an extension, so let's say the semi-direct product extension so this is a very special extension, is given as following, is given as, so I'm going to tell you what the multiplication is. You can check that it's defines a group structure. So as a set, is given as a set by A cross G. However, because G acts on A, the multiplication is going to be twisted by that. So it's not just going to be the direct product of groups. With multiplication, so A comma G dot A prime G prime. This is A plus, so when I try to move this past here, it's going to multiply on A prime. And then G and G prime will just multiply as usual. Okay, so the multiplication in the semi-direct product takes into account the action of G on A. And you can check that using the fact that this is really a G module, that this becomes a group. Okay? And so fact, easy to check, to give an isomorphism of an extension. Let's see, which way do I want to do it? Yeah. So I have this semi-direct product. It obviously surjects onto G. I just forget the A component. The kernel of that's obviously A, so that's an extension. So that's an extension. To give an isomorphism of this extension with some other one, like that, is the same as to give a section of this. Right? I know where the A bit maps. I just have to tell you where the G bit maps. Okay? So to give an isomorphism like this is to give let's call this Q for quotient, is to give a homomorphism S such that it's a section. So SQ should be the identity on G. Okay. So that's called a splitting of the extension. So it's called a splitting. And a typical extension might not have a splitting. We'll see non-split extensions as we go along. So not every extension is isomorphic to a semi-direct product as an extension. And so our goal is to find some way, given G and given A as a G module, to find some way of classifying up to isomorphism all these extensions. And this is one thing that the cohomology will be useful for. So this one I'm going to save because the answer to our problem is on that board, actually. Okay, we have 25 minutes. So let me at least try to define everything so I can state the main result, and then we'll have some details to check in the seminar. So the goal given a group G and an A module, classify extensions of G by A up to isomorphism. And the idea is the following. So we know that the trivial one is the one for which there's a section as a homomorphism. Now, if I forget that the extension is of groups, and I just think of G tilde and G as sets, then of course there's a section. I just choose a preimage of every element. Okay? Won't be in general homomorphism, but I can, choose a preimage of every element. So the idea is the following. So given an extension, G tilde G 1 A 0. So let me give this as a definition. A base section, this is what I'm defining, is a section of Q, so S G to G tilde, of Q as a map of sets, so not as a homomorphism, such that, so the base part is I don't care which preimage I choose for all the other elements, but I will be careful about choosing the preimage of 1. I know there's a preferred preimage of 1, namely 1. Okay? So that's a base section. And base sections can be used to describe the multiplication in G tilde. Okay. So note, I'm just emphasizing this, it's a section as a map of sets, not necessarily as a map of groups. So note S, a base section, S is not, in general, a homomorphism. If it were, then the extension would be split, and not all extensions are split. So let's define a two cochain from it. So let's define its failure to be a homomorphism. So let's look at S of G1 times S of G2. If this were a homomorphism, that would be the same as S of G1 times G2, and so the difference would be trivial. But in general, this difference is not trivial. It measures the failure of S to be a homomorphism. So I'm going to call that sigma of G1, G2. Okay. And note, if I evaluated, if one of these elements is 1, then this is 1. Okay. So let's note the following. S of G1 equal sigma of G1 equals sigma of 1G equals 1. And sigma, which I can think of as, so that's 1 in G tilde, which is the same as kind of 0 in A. If I think of A as a subgroup, mapping into G tilde, where 0 goes to 1. And also, note that this is always, what happens if I apply Q to this? Well, I'll get G1 times G2, and then the inverse of G1 times G2. So this will equal 1. So it's in the kernel. Therefore, it's in A. Okay? So this thing which measures the failure of S to be a homomorphism is actually a two cochain. So sigma is a normalized two cochain of G with coefficients in A. So far, so good. And what we want to argue is that this data more or less classifies the extension, but up to some ambiguity, that ambiguity will be a coboundary. Sorry, I showed that this was a cochain. I need to argue that it's a cocycle. This is a normalized two cochain. And I claim that it's a two cocycles. So that will be a calculation that we have to do. Let's try to do it. So claim is that sigma is a two cocycle. Okay, and we have the formula for a two cocycle that we have to check, right? So we need to compute this. So let's try to do it. And the only confusing thing about it is there's a bit of ambiguity of notation. If I think of A as an abelian group, and the group operation is plus, then I get, well, plus and minus. But inside of G tilde, I write things multiplicatively. So we'll have to play off these two. This is how Weibull does the notation. There's maybe an alternative, but I'm going to do it this way, even though it's a little confusing. So let's try to compute this. So we need to compute, I could move, well, I just need to compute this expression and see if it's 0 or not, where alpha is sigma. So let's write it out. So let's check it. Let's write G1 times, so that's acting on sigma of G2, G3 minus sigma of G1, G2, G3 plus sigma of G1, G2, G3. That was plus minus sigma of G1, G2. Okay. And let's write that out using our expression for what sigma is. Okay. And we'll have, because we're computing inside, all of this lives in A. All of this lives in A, so we'll be able to kind of rearrange terms because it's a Boolean. So first of all, this is the action of on A as a module. So this is S of G1, that's some lift, times whatever is in the middle, and then times G1 inverse. Remember, that's how the action of G on the kernel was defined. And then this expression is S of G2, S of G3, S of G2 times G3 inverse. This is, by definition, S of G1, G2, S of G3, S of the triple product, G1, G2, G3 inverse, plus S of G1, S of G2, G3, S of G1, G2, G3 inverse, minus S of G1, S of G2, S of G1, G2 inverse. Okay, and now we have to rearrange these in such a way that everything cancels. So let's look at it. I always have to stare at it for a moment to see. So what could cancel with what? It looks like probably I can cancel some of these by interpreting this minus as inversion in the group G inverse. All right, just a sec. Right, so if I interpret this as inversion, and this is, I can rewrite this term. I can rewrite this term as S, so this all will be equal to I'm going to rewrite this term going to do it. maybe I'll rewrite this one also with an inverse. So this will be S, G1, G2, G3, S, G3 inverse, S, G1, G2 inverse. This one is what it is. And this one I'll rewrite as plus G1, G2, S, G2 inverse. Okay. And now it's abelian. I can put them in any order I want, and I can replace pluses with just multiplication inside G tilde. So let's try to do that. So what can cancel? So if I multiply this on the right by here, these two terms will cancel. If I multiply this on the right here, a bunch of stuff will cancel. So let's try to do that. Okay, so if I do these two together, I'll get S of G1, S of G2, S of G3, S of G2, 3. So this will cancel with this, and this will cancel with that. So I'll be left with S of G1, G2, G3 inverse. And if I put these two together, this will cancel with that. So I'll have a plus S G1, G2, G3. Then S of G3 inverse. S of G2 inverse. S of G1 inverse. Okay? And now I multiply these two together. This will cancel with this with this with this, and that with that. Okay? So this is 0. So this is elementary. The only confusing thing is we write the operation in A in two different ways, either as a plus or under this homomorphism as a multiplication. Okay. So indeed, this is a two-co cycle. And what? Very good. So that's claim 1, which we just checked. Claim 2. Suppose, what did I do? I started with an extension. I chose a base section. A base section always exists, and from that I got a two-co cycle. What if I chose a different based section? I would get a different two-co cycle. How are they related? So the claim is that for a fixed extension, two different base sections, if S and S prime are two base sections, then the corresponding two co-cycles sigma and sigma prime differ by a coboundary. And so they define the same cohomology class. So let's do this calculation. And then I'll state the main proposition, and we'll finish the details in the seminar. Okay, so indeed, let's check this claim. So suppose I have two base sections. So if S and S prime are base sections, then there is a one cochain, let's call it beta, so normalized, such that S of G equals beta G times, so I interpret that as an element of A and therefore as an element of G tilde. And that's just because if I take the difference between these two, it lives in the kernel, therefore in A. And if I evaluate it on G equals 1, they have no difference because they're based. And so beta of 1 is 0. Okay? So the claim is that this beta, its differential, will give the difference between these two things. Okay? So now, let's compare sigma to sigma prime. All right, so let's check. Let's just compute. What is sigma prime of G1, G2? So by definition, it's the failure of S prime to be a homomorphism, right? So it's S prime of G1, G2, S prime of G1, G2 inverse. Okay, and let's write that out in terms of, yeah, maybe I wanted to write it out the other way. Yeah, okay, let me write out the other one like this. So there's sigma and S. But I know I can express S in terms of S prime via beta. So let's spell that out. So this is what? This is going to be beta of G1 times S of G1, beta of G2, S of G2, beta. So what is this? This is going to be, S prime. This is going to be S prime of G1, G2 inverse times beta of G1, G2 inverse. This is this whole expression inverted. And then finally, I want to insert here I want to insert here an S prime of G1 inverse times an S1 prime of G1. Okay. So let me write this as beta G1 S prime G1 times, so let me put it in brackets to make it cleaner to read. So I'll insert this term and then cancel it out. Well, that's just like in calculus when you put in a plus minus epsilon in the middle of some expression. Okay. And I'll continue on this board. So if I've done things right, we can now rewrite everything additively, and we should see that sigma and sigma prime are differing. By a coboundary. So let's look at this. This is an element of A. This is conjugating an element of A by a group element. So since A is normal, that remains an A. So this is an A, this is an A. I'm afraid I missed a term somewhere. Yes, this one. I forgot to write it here. Sorry. That one is supposed to be there to cancel stuff. This one is to be there, was here. Okay, so this is an A, this is an A, this is an A, this is sigma prime of G1, G2. And this term is also an A. So I can rewrite everything as addition inside of A. So this is what? This is beta G1 plus. This is the conjugation action. So this is G1 dot beta G2 in the module action. The next term is sigma prime of G1, G2. And then this extra term, beta of G1, G2. Inverse, which in the group A is a minus. Right? And so what is this altogether? This is sigma prime plus d beta evaluated on G1, G2. Because if I look at these three terms, that was exactly our expression for a two coboundary. Okay. So that implies that this sigma equals sigma prime plus d beta. And so they have the same cohomology class. Okay. And now I can write the proposition, or maybe even theorem. And we're over time anyway. So the theorem is the following. We have extensions of G by A with base section up to isomorphism that respects the base section. This will be in bijection with these reduced cocycles. From the reduced cocycle, I get a cohomology class. And we just saw that that was independent of the base section. So I could just pass to extensions of G by A, again, up to isomorphism. So I will get a map like this. That's what we just checked. And the interesting thing is that this is an isomorphism. Okay? So we've constructed this map. And we're pretty close to showing already that it's an isomorphism, but we're out of time. So we'll finish that in the seminar. We'll also compute some examples in the seminar. Okay, I'll stop there.